Today we're going to continue our history lesson about matter, particularly the atom, by moving forward from John Dalton. John Dalton, remember, proposed that everything is made up of atoms, that the atoms are indivisible and they're very small. You can't change one atom to another, you can't destroy them, you can't create them, and that compounds really only are just combinations of different numbers of atoms. And a chemical change then is just a rearrangement of the same atoms that were always there. One of his postulates had a bit of a problem, and that is the one about atoms being indivisible. It turns out that atoms are made out of smaller things yet, and there were two people who really played a significant role in uncovering what those particles are. The first one was J.J. Thomson, who is shown here in this picture with a device called a Crooks Tube. This is the basic idea behind a Crooks Tube. A Crooks Tube is just a sealed up tube made of glass, typically, so you can see what's happening inside. Sealed into one end of the glass is a thing called a cathode, and it's just a metal plate that happens to be hooked up to a negative electrical terminal, like on a battery. And then on the other end is something called an anode, and the anode is hooked up to the positive terminal of the battery. A sort of a glowing light seems to appear when you hook this thing up to electricity. And here you can see that this actually casts a shadow. This iron cross here is maybe a metal or something like that. And when you look on the end of the tube, you can see that the whole thing is glowing green, except where that piece of metal is. It casts a shadow. This is a picture of Crooks Tube in operation, and you can see the end of the thing has got this greenish glow to it, and it's again casting that shadow. Well, most people thought that that was some kind of light, like it was energy, but J.J. Thomson was able to show that that glow is actually caused by a stream of particles hitting the end of the tube. So it wasn't energy, it was actually matter. Another thing Thomson was able to do with his Crooks Tube was he introduced charged plates into the particle stream. So if the stream of particles are coming through here, he's got a plate here and a plate down here, and these plates are connected to terminals. So he could make this positive or negative, and he could do the opposite down here. When he did that, he found out that the particles always bent toward the positive plate. So if the positive were up on top, like shown in this picture, the stream of particles, as it went through that charged plate zone, would bend toward the positive. And you could reverse the polarity, put the positive down, then the particles would go down. And you could tell this by where the glowing spot was on the other side. Without charged plates, it would just go straight towards the end.
These are the charged plates in a cathode ray tube. Here's one that's on the top. Here's one that's on the bottom. And a stream of electrons comes through that point there. Inside of this case, there's a high voltage grid and a little device that gives off electrons. The electrons see the high voltage, they get accelerated, and some of them pass through a small hole in the center. The ones that pass through come and they will hit a screen. And when those electron beams hit the screen, causes it to glow. If I were to apply a positive voltage to the top plate, as the negative electrons went through, they would be deflected. They would go upwards as a result of that positive voltage. On the other hand, if I were to put a negative voltage on the top plate, the electron beam would go downwards as a result of that. I can alternate the beam electrically, alternately going up and down by altering the positive and negative aspect of that beam. This is the fundamental principle in the operation of television. I get a device that causes it to deflect up and down, vertical. I can also do the same thing horizontally with two more plates that control the horizontal axis. And by combining the two, I get 45 degrees. Now, as the charged particle travels through the air, kind of it acts like an electron going through a wire inasmuch as it creates a magnetic field around it. If I were to bring a magnet nearby, I could deflect the beam with a magnet. Electricity and magnetism inexplicably connected.
Well, Thomson had to come to two conclusions about these little particles that he called electrons. One of the conclusions is they came from atoms. There's nothing else in the tube except atoms, and so these electrons must have been extracted from the atoms. Electrons are part of what atoms are, then. The other thing that he had to conclude is that they're negatively charged. Because they moved toward the positive plate, and because opposites attract electrically, and every physicist, including Thomson, knew that, these particles must be negatively charged particles. So that means the atom contains smaller particles yet that are negatively charged. This required a new view of what the atom was. Instead of being just a solid little sphere like a BB, it had to have been made of parts. So Thomson names these things electrons, and he comes up with a new model of the atom. And this comes to be called the Plum Pudding model of the atom. Let's see what it looks like. His idea is that you will have inside the atom some negatively charged particles, little tiny bits that are negatively charged. Not very large. He knew they weren't very big compared with their charge. The rest of the atom, he thought, must be this positively charged kind of a mush. You could think about it as little specks of negatively charged sand in a glob of jello, sort of. The jello is positively charged, the sand is negatively charged. It was called the plum pudding atom because of an English dessert called the plum pudding that was popular at Christmas time. Here's a picture of a plum pudding. The closest thing we have to a plum pudding is something like a raisin bran muffin. If you break open a raisin bran muffin, you see that it's mostly dough, this kind of not very dense dough. That's like the positively charged mush. And then the raisins that are scattered around in that muffin, or the bits of plum that are in a plum pudding, well, those things are the electrons. He didn't call it the plum pudding atom, but some other people named it that because it reminded them of a plum pudding. The next advancement in the understanding of the atom came from a guy named Ernest Rutherford. Rutherford was actually a student of J.J. Thomson's, and when he became a scientist in his own right and began doing his own experiments, he stumbled across another thing that was true about the atom. When he made this discovery, Ernest Rutherford was studying something called alpha particles. Alpha particles aren't really important to this story except for the fact that they have two characteristics. One is that they're positively charged, and that's the opposite of electrons. And the other thing is that they're much, much heavier than electrons, on the order of like 10,000 times heavier than electrons. This is his experimental setup. What he was doing was he was trying to figure out what would happen to alpha particles when they interacted with atoms. And so he wanted to have as few atoms as possible. So he selected gold, because you can smash gold into a very, very thin sheet called gold foil or gold leaf. And he was bombarding this gold foil with alpha particles. So an alpha particle source was over here. It would fly through the gold foil, and then he had this screen that would show a little spark anytime a charged particle, like an alpha particle, hit it. And then he was looking for these sparks. And this was a movable screen, so he could slide it back and forth and put it in different places and try and find out where most of the sparks were happening. In other words, where were the alpha particles going? Now, Rutherford believed in the plum pudding model of the atom, and so this is what he thought the gold atoms that he was shooting the alpha particles were like. Remember, globs of jello with negatively charged grains of sand in them is the basic idea of the plum pudding model of the atom. And the alpha particle is much bigger than the electrons, the grains of sand, and positively charged, unlike the electrons. So with our glob of jello and grain of sand analogy, this is like shooting bullets at jello balls with sand in them. So here's what he expected would happen. He thought most of the sparks would happen right on the opposite side of the gold foil. They'd mostly just go straight through the positively charged mush and hit the screen on the back. He thought it might be possible that he could get a few sparks deflected off to the side if they happened to go in just the right spot and be attracted towards the negative specks of sand, the negatively charged electrons. But here's what he actually found. When he bombarded these alpha particles, he found that in some cases the alpha particles actually bounced back and left sparks on the screens that were behind the gold foil. Rutherford was extremely surprised by this, and he wrote in his journal, "It was quite the most incredible event that ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Or like you shot a bullet at a glob of jello with grains of sand in it, and it bounced off the glob of jello and came back and hit you." Here's another way of thinking about why this was a surprise to Rutherford. Imagine a car going 60 miles an hour down the road encountering a mosquito. Watch this scenario. The mosquito hits the car, and the car bounces off the mosquito. That's sort of what we're talking about here, because an electron is about as much less heavy than an alpha particle as a mosquito is than a car. So this demanded a new way of thinking about the atom, a new atomic model. Here's how it had to change. Something in the atom must be positively charged. Rutherford calls this thing a nucleus. The nucleus is positively charged, and compared with alpha particles, it must be heavy enough that they would bounce off it, like a mosquito would bounce off of a car. So now the new model is like there's a shot put in the middle of the jello, a glob of jello around that with specks of sand. And what was bouncing the alpha particles back was that nucleus in the middle, heavy, positively charged center. So the new model of the atom looks like this. Electrons on the outside, mostly empty space in the middle, he thinks, and then a lot of positively charged mass in the middle called the nucleus. So here's his new idea of what he was shooting the alpha particles at, and this explained what happened in his experiment. So his experiment was a good test of this theory. The test actually happened before the theory. The nucleus, he thought, must have a positive charge that equals the negative charge of all the electrons. So if you had an atom that had 8 negative charges from 8 electrons, the nucleus would have to have a +8, because he knew that atoms were neutral. Everybody knew that. Well, another advancement came when James Chadwick, who was actually a student of Rutherford's and worked in the same lab as J.J. Thomson, discovered that the nucleus actually is made up of even smaller particles yet. The nucleus is made up of protons. Protons weigh about 10,000 times more than an electron, and they have exactly the opposite charge of an electron. So electrons are negatively charged, protons are exactly as positive as an electron is negative. The other particle that's in the nucleus is called the neutron. Its weight is also about as much as 10,000 electrons, so approximately the same as a proton. But it doesn't have any charge at all. So the emerging atomic model now has a nucleus that has a number of particles in it. Some are neutrons, some are protons, and then surrounding that nucleus is a number of electrons which are all negatively charged. The number of protons and electrons are the same in a neutral atom. Not all atoms are neutral, but that's the way we're going to think about them for a while now. The number of neutrons, however, can vary from atom to atom. So it's the number of protons that's in the nucleus that determines what element the atom is. If it has 1 proton, for example, it's always hydrogen. If it has 6, it's always carbon. If it has 26, it's always iron. That number, the number of protons, is called the atomic number. And that's listed on the periodic table. In fact, it goes in order of atomic number. So this is what we would think an atom of hydrogen would look like under Chadwick's model. Hydrogen is atomic number 1. It has 1 proton and 1 electron. Oxygen is number 8. So it would have 8 protons in the middle. Count them. 1, 2, 3, 4, 5, 6, 7, and there's a little 8 back in there. Some neutrons, it doesn't really matter. And then it would have 8 electrons on the outside. That's what makes it oxygen, the fact that it has 8 protons. Carbon, 6 protons. 1, 2, 3, 4, 5, 6. That's what makes it a carbon atom, the fact that it has 6 protons. The neutrons are immaterial. And actually so are the electrons. What makes it carbon is that it's atomic number 6.